Zoom will be confused about the time. I think it starts at 9:15. Anyway, welcome. Thank you for giving this talk. And I would say the floor is yours.
Okay, thanks. So I was asked to give an introduction to Iwasawa theory, and I wasn't exactly sure what the background is. So what I'm going to do is kind of just give an abstract formulation of what a main conjecture in Iwasawa theory looks like, then with some examples, followed by some more recent kind of developments in non-commutative Iwasawa theory, or even in the sort of looking at modules which are pseudo-null or smaller. Okay, so here it is. So the way I look at Iwasawa theory is it's a tool for proving relationship between arithmetic invariants and analytic invariants. Okay, so number theory is full of conjectures which relate arithmetic to invariants to analytic invariants. One family of such conjectures are the Bloch-Kato conjectures or the Tamagawa number conjectures. Okay, and Iwasawa theory is a kind of systematic tool for proving such results. So typically such a result is codified in what is called a main conjecture of Iwasawa theory. So in any particular situation, you will have main conjecture for that particular set of objects, which codifies this, which makes precise this relationship between arithmetic and analytic invariants. Typically, this involves sort of an infinite family of objects, and then the analytic invariants and arithmetic invariants you put in this, they come in this infinite family, and you hope to prove that the invariants coming from two sides are equal in some sense. Okay, so let me describe this in a particular situation, but also abstractly. Right, there's no real arithmetic here. It's just some the kind of relationship one expects in Iwasawa theory. Okay, so let's go to the very classical situation where you look at gamma is your group ZP. So p-adic integers with addition as the operation, but I'll denote gamma by multiplicative. Okay, so that's the standard convention. Lambda is the completed group ring ZP double bracket gamma. So it's this n should be under the arrow. So this inverse limit is over n. ZP gamma mod gamma to the Pn. Okay, so I'm denoting gamma multiplicatively. So this is the quotient whose order is p to the n, and you look at all these group rings, you take the inverse limit in a natural way, and that's the completed group ring. Okay, this is the so-called Iwasawa algebra, lambda, and one can show that it's isomorphic to power series ring in one variable over ZP. So this isomorphism is not canonical. It depends on choice of a topological generator of gamma. So once you fix a topological generator, this is the map that takes the topological generator to t plus 1. Okay, so that's the isomorphism. This is the most classical Iwasawa algebra that one looks at. So on the analytic side, what we do, I mean, later on, I'll replace this gamma by more general groups. Okay, so if you want, you can think about a more general group here as well. So so R is the set of all finite dimensional continuous representations which are QP valued. Okay, so in this case, of course, we will just have abelian and then direct sum of abelian representations. But if it's a non-abelian group, then we can have irreducible representations which are not one-dimensional. In any case, R doesn't just have irreducible representation; it has all finite dimensional representation, and A is some subset of R which is dense. Okay, so dense in the p-adic topology, in the obvious sense that going modulo higher powers of P, you can approximate any element of R. So for example, all finite order representations of gamma can be, the set A can be all finite order representations of gamma. Okay, so that's dense in all representations. All right, so so for each row in A, you have some p-adic number A row. Okay, so this is, and this satisfies some properties. So if you take the one attached to rho plus rho prime, you get product of A row and A row prime. So these A rows will be some L values, and L values satisfy this kind of product. By Artin formalism, they have this kind of product expression. So this is what you you want it to satisfy. So when we actually get to an example, these A rows will be L values. But right now it's all kind of abstract situation where you are given some p-adic numbers. Okay, so this is the kind of analytic side. On the arithmetic side, you will have some arithmetic objects. So typically a Selmer group, okay, ideal class group, and so on. So on the arithmetic side, you will have a finitely generated torsion lambda module. So what does torsion mean? Torsion means that, so most kind of down to earth explanation is for every x in X, there is a non-zero divisor. Of course, lambda here is integral domain, but in general, a non-zero divisor lambda, which annihilates X. Or another way of saying this is that X is supported in codimension 1. Or another way of saying that is X tensored with the total ring of fractions of lambda is actually 0. Okay, so these are some equivalent ways of saying that X is a torsion lambda module. So okay, so on one side you have analytic objects which will be L values, and on another side you will have some arithmetic objects, typically a Selmer group. So so most classically, how does one attach an invariant to X? You use what is called structure theorem for finitely generated lambda modules. So this is simply a generalization of structure theorem that one learns for PIDs. So X, there will be a map from these cyclic modules lambda mod Fi into X, which is a pseudo isomorphism, meaning that the kernel and co-kernel are finite. Okay, and because X is torsion, these things will be non-zero in this particular case. Of course, in general, for a finitely generated lambda modules, you can have a bunch of copies of lambda also. Okay, so the characteristic ideal of X is defined to be the ideal generated by product of Fi's. Of course, these Fi's themselves are not well defined. For instance, you could have lambda mod F squared or lambda mod F times lambda mod F and so on. So those can be pseudo isomorphic, but the product of these Fi's, this is well defined, and I mean it's the ideal generated by product of Fi's that depends only on X. And we call it the characteristic ideal of X. Okay, and a generator of this ideal is called a characteristic element. Okay, or a characteristic power series in this case, because remember we had an isomorphism of lambda with power series ring in one variable. Okay, all right. So on the other hand, if you have any continuous homomorphism from gamma to QP bar, we can extend it to a map from lambda to QP bar. Okay, so QP bar cross, and we can extend it ZP linearly like this. All right. So what does the abstract mean conjecture say? And sort of I learned this point of view from David Burns. I'll attribute this kind of way of thinking about mean conjectures to Burns. Says that there exists an element psi in lambda which satisfies two things. Okay, on the one hand, it generates characteristic ideal of X. Okay, and on the other hand, it interpolates all these A rows for all the rows in A. Okay, for all the rows in this math fac A. So it's an arithmetic invariant which is related to L values. Okay, right. I mean that's kind of how one that's what the main conjecture looks like, and if you have seen this wouldn't be surprising at all. The statement. Okay, so Iwasawa main conjecture. This is so. Next I'm going to give you some examples of the main conjectures that are well known. So the most classical is Iwasawa main conjecture. This is for totally real number fields. Okay, so let F be a totally real number field. I mean, this is of course no longer a conjecture. It's a theorem for over 30 years now. Due to Miser whiles and whiles, and I'll say that in a minute. Okay, so H be a finite abelian CM extension of F, and just I mean some of these things are for simplicity, but of course we can now formulate them and even prove them more generally without these assumptions. But in the most classical setting, when it was first made, you had various assumptions like P does not divide the order of H over F. Mu P is contained in H. This is just a simplifying assumption. Here mu N denotes the nth roots of 1. Okay, so let chi be an odd character of order prime to P such that if I take the, sorry, this should have been H bar. Yeah, maybe this is just my notation. This H upper chi just means H bar fixed by kernel of chi. Okay, so this does intersects trivially with the field generated by all P power roots of 1 over F. Okay, again, this is some simplifying assumption. Otherwise, I have to introduce poles for my p-adic L function, and the statement is just somewhat more complicated. Okay, so what is the arithmetic side? What you do is you take the maximal abelian unramified pro P extension of H mu P infinity. Okay, and you let X be the Galois group of M over H mu P infinity. Okay, so you have H, then you have the H mu P infinity, and over that you take the maximal abelian unramified pro P extension of H, and I call it this script X. And what I'll do is I'll take the chi component of it. So I tensor X over ZP with ZP chi values, the ring obtained by attaching values of chi to ZP, and I take the chi component of it. Okay, so if you like E chi times this module, and this is one of the reason because I wanted to define my X this way. This is one of the reason why I assume that this should have been F bar to the kernel of chi. Sorry. So this is one of the reason why I assume that my chi has order prime to P. Okay, then Iwasawa proved that X is actually a finitely generated torsion module over this ring. So this is not ZP double bracket gamma as I had in the abstract main conjecture, but some finite extension of ZP double bracket gamma. So again, the same kind of theory applies. Right, so and Iwasawa proves that this is finitely generated and torsion. So this essentially follows from classical theory. Okay, all right. So this is my arithmetic side, a concrete arithmetic object. So I can attach characteristic ideal to this X, and now I want to describe a specific generator of this characteristic ideal using L values. Okay, so what are the L values in this case? So chi cyclotomic, chi cyc, this is the p-adic cyclotomic character of F. And what I do is, so what is my set A? A is all powers of this cyclotomic character. So chi cyclotomic to the n, where n is divisible by p minus 1. So these are all positive powers divisible by p minus 1 of this cyclotomic character. And you can show that this is actually a dense subset of all the characters of gamma. And what are these L values in this case? These are just the usual complex L value at 1 minus n. So this is a non-zero algebraic number, right? So chi inverse is still odd, and then omega is the tachymeller character, so that's odd. So their product is even. You're taking L value of an even character at odd negative integer. Remember that p minus 1 is even because p is odd. And then you remove Euler factors at primes above p. So this you need to be able to periodically interpolate these L values. If you did not remove Euler factors at p, you wouldn't get anything that's periodically continuous. Okay. So on the analytic side, first Kubota-Leopold over yeah, they should be dash, not equal to Kubota-Leopold when f is equal to q, and in general by Cassanogas and Deligne-Ribet, they prove that there exists an element in this group ring which interpolates all these values. Okay, so what this amounts to is showing some congruences between these values. Okay, so you need to show some what are called Kummer congruences between these L values, and if you have those congruences, you get an element in the group ring. If you haven't seen this before, then maybe what you have seen is if you want an element in the group ring ZPG, which interpolates particular values when you evaluate at each character of G, you need those values to satisfy some congruences. Okay, otherwise you will simply get an element in QPG rather than ZPG. So congruences is what it implies integrality property, and so this is similar, but over completed group rings. Okay, so the congruences are somewhat more complicated, and these are the congruences that Deligne-Ribet Cassanogas prove. Okay, so now you have two sides. You have your
If you forgot the L after the chi sig n, right? It should be this thing applied to L.
Sorry, I couldn't hear you very well.
So I think that the L plays a role, but I think it should be chi sig n evaluated on L, right?
Yeah, so yes, sorry, there should be an L here, right? Yeah, sorry. Right, L evaluated at this thing. Yes, I'm very sorry. This is a typo. Thank you for catching it. Yeah. Right. Sorry about that. Okay. Yeah, somehow it just got completely erased. I don't know why. Okay, so Iwasawa mean conjecture, which is now, of course, a theorem of Mazur and Wiles for f equal to q and Wiles in general, and then for f equal to q, Ribet gave a different proof using Euler systems. It says that L is actually a characteristic element of X. Okay, so this is precisely the abstract formulation of mean conjecture that we saw. It looks like this in this precise arithmetic setting. Okay, so characteristic ideal of X is generated by L, and it interpolates all these L values that we have. Okay, so L of chi cyclotomic to the n is an. Okay. So this is the second example, and I'm going to be even less precise here. So E over Q be an elliptic curve, and let P be a prime of good ordinary reduction. And so just to be safe, and because I'm not making a precise statement, I don't even have to say that it's bigger than or equal to 5. But in any case, at P equal to 2 and P equal to 3, you have to be more careful, I guess. So. Okay, so let K be the cyclotomic ZP extension of Q. So again, I'm in the situation where the Galois group is isomorphic to ZP, and X in this case will be the dual Selmer group. Okay, so this is Selmer group over this infinite extension, and I take the Pontryagin dual of this. So this is the so-called dual Selmer group. Now I should have, ideally I should write down all the kind of attributions, but yeah, in this case, Mazur conjectured that this X will be a finitely generated torsion lambda module, and this was proved by, so for CM it's kind of older, proved by Coates and Wiles, and then for non-CM elliptic curves, this was proven by Kato using his Euler systems. Okay, so on one hand, you have this arithmetic object to which you can attach characteristic element because you know that it's torsion, and on the other hand, you take what is your A? You take this to be all finite order characters of your gamma. So this is what I was saying, that if you take A to be this particular thing, again it's dense. And the values are these values of L functions attached to rho, attached to E twisted by rho. Okay, so these are the L functions of E twisted by rho, and you evaluate them at 1. Okay. All right. So again, I'm not writing down all the sort of the precise statements that there exists a p-adic L function which interpolates these values, and there are kind of various constructions in various cases for these p-adic L functions. Okay, so I'm not going to say too much on this. All right. So, but anyway, these are the kind of objects that one relates using main conjecture of Iwasawa theory for elliptic curves, and a lot of progress has been made on this particular main conjecture thanks to Kato and Skinner, Urban, and so on. So, in most cases, we know this main conjecture to be true. They have some technical hypotheses on various things, but I believe for p bigger than or equal to 5, it's kind of almost known. So yeah, all right. So that's second example of a main conjecture. But this is a very classical setting, okay, and we want to go beyond it. So so one of the things here is that this formulation of main conjecture uses structure theory for finitely generated lambda module. So if lambda is not if lambda is not Iwasawa algebra of ZP, but even if it's Iwasawa algebra of ZP times some finite group with order divisible by P, then we don't have such a clean statement for structure theorem. Okay, we don't have this, and so we would like to we would still like to formulate a main conjecture and then see what we can prove. And this is usually referred to as equivariant Iwasawa main conjecture or equivariant main conjecture. So you don't just take ZP extension, you take you take ZP cross some finite group, and of course that finite group will only be interesting if the order of that finite part is divisible by P. Otherwise, that finite part will decompose character-wise. Okay. All right. So let's take another look at the characteristic element. So you have this kind of pseudo resolution, right? It's not actually resolution of X because this map is not surjective. It has finite co-kernel. I mean, this is not a standard term. I'm just kind of motivating this. So you have this kind of resolution, and characteristic ideal is the ideal generated by determinant of this map. Sorry, there should be brackets here because it's, yeah, this is an ideal. So it's ideal generated by this thing, right? So this suggests another way of defining a characteristic element without using structure theorem. Okay, and this is what I'm going to describe more precisely rather than sort of this non-standard way. And this thing generalizes to other rings, not just ZP double bracket gamma. So what you do is you take a bounded resolution of X by finitely generated projective lambda modules. Of course, in this case, projective is same as free, and so that's what I'm taking. Because X is torsion, what this means is that C tensored with the total ring of fractions of lambda, this complex is actually acyclic. Okay, and if you have acyclic complex, there is a canonical isomorphism from determinant of that that complex to Q lambda. Okay, so I mean, I'm going to be vague here about what notion of, this is determinant over Q lambda. Should have been here, I suppose. Yeah, anyway, I'm using the Mumford-Knudsen determinant, definition of determinant, if you like. Okay. Later on, I may write determinant over non-commutative rings as well. So there's construction by Deligne that I'm going to use without saying what it is, just like here. Okay, so if you have an acyclic complex, then if you have a exact sequence, bounded exact sequence, then you can write down, you can get a canonical isomorphism between determinant of that complex and the ring itself. Okay. On the other hand, because this complex C has Euler characteristic 0, okay, you can actually show that there exists. Yeah, so this det sub R always comes like this. I don't know why, not here, but here. Okay. Yeah, so you can actually show that there is an isomorphism over lambda itself with determinant of this complex and lambda. Okay, and there's nothing canonical about this isomorphism. You just know that there exists such an isomorphism. Okay, so there are sort of many such things, as many as the units in lambda. So this psi is well defined only up to a unit in lambda. All right. Okay. Nevertheless, we can extend scalars for psi, which I'm again going to denote by psi itself. Compose it with the canonical isomorphism inverse, and you get an isomorphism from Q lambda to Q lambda. Okay, so it's an isomorphism from Q lambda to Q lambda, and so it's given by multiplication by an element of Q lambda. Okay, this is a lambda algebra isomorphism. So it's multiplication by an element, a unit in Q lambda. Okay, so a non-zero element, and this gives the characteristic element of X. Okay, so this is a way of defining characteristic element of a finitely generated torsion lambda module without using structure theory. Okay, and this works over more general rings as long as you have a finitely generated torsion lambda module. Okay, now I'm going to give a slightly different point of view on this again. All right, but perhaps yeah, so as soon as you see determinants and so on, you can guess that K theory is going to come into picture, and there are various presentations of this K1 group and so on, which I'm not really going to go into, but I'm just going to say that there's this exact sequence coming from K theory. So K1 of lambda goes to K1 of Q lambda, and then there's the boundary homomorphism to the relative K group, and one can show that this actually is surjective, right? I mean, in this particular case, it's of course very easy because the next term in this is K0 of lambda, and then after that it's K0 of Q lambda, and they are both Z, and you know that map is just that map is an injection, right? It just takes 1 to 1, right? I mean, it's Z because it just counts the rank of the module. Anyway, so this is surjective, and having a finitely, so what is this K0? Okay, so this K0, this is the relative K0 group, and it's defined as Grothendieck group of the category of bounded complexes of finitely generated projective lambda modules with torsion cohomology. Okay, so for example, the C has a class in this relative K0. Okay, because that's also a bounded complex of finitely generated projective modules with torsion cohomology. So torsion cohomology, again, just to remind you, it means that the complex becomes acyclic once you extend scalars to Q lambda. All right. So we can define, so we can take class of such a complex in here, and we can define characteristic element of that, that complex to be any element in K1 of Q lambda that maps to this class. Okay, so this is this short exact sequence is kind of encapsulating everything that is said on this slide. Okay, that's it. So any element in Q1 K1 of Q lambda that maps to the class of C is called a characteristic element of this complex C, or if this is the resolution of X, then of X itself. Okay. All right. Yeah. So that is so now we have removed any structure theory, and we can actually do this for general, sort of more general Iwasawa algebras. And what I'm going to tell you about is how what exactly is done for non-commutative non-abelian extensions. Okay, so when gamma is replaced by a non-abelian group. So the kind of the most satisfying description that we have is for only certain kinds of non-abelian groups. Okay, so what we do is we replace our ZP by a compact p-adic Lie group. Let's say something like GL2ZP or GLNZP or something like that, which has a quotient isomorphic to ZP. Okay, so G has a quotient gamma which is isomorphic to ZP, and then I denote the kernel by H. So in this particular case, we have a very satisfactory description of what a non-commutative main conjecture in Iwasawa theory looks like. Otherwise, we can define, I mean, there are ways to formulate Iwasawa main conjecture, but they are somewhat kind of more abstract, and it's not clear how to actually prove anything for them. Okay, all right. So so again, I replace my gamma by G and my lambda by that I had earlier by the completed group ring now of G. Okay, so this is lambda G, which is inverse limit of these group rings. And here U runs through all open normal subgroups of G. Okay. So what I do is I take this particular subset of lambda, which are all elements of my ring, such that lambda mod this small lambda is a finitely generated lambda H module. Okay, so H is again a profinite group, right? So I can define completed group ring for lambda for H as well, and that I call lambda H. So this is Iwasawa algebra of H, and what I want is that this element, the quotient by this element of lambda is a finitely generated lambda H module. So if you like an example, so in our earlier situation, what will the set S be? This will be all elements in the power series ring ZP double bracket T, all power series which are such that the coefficients of those power series are not all divisible by P. Okay, so S will be complement of the ideal generated by P in that particular case. Okay. And yeah, just because I want P in there, I'll just throw in P and take the multiplicative set generated by P and S. All right. And why does one take this particular S? Well, for two reasons. First is that you can actually localize this non-commutative ring at S star or S. So S or S star satisfies this OR condition, left and right OR condition, and so on. And so you can actually just localize it as if this were a commutative ring, and it's all fine. So that's one reason. But you can, I mean, you can also do it with the total ring of fractions of lambda G. So why not take that instead of taking this complicated set S? So the reason is that if you take modules which are torsion and twisted by some character, then that module may not be torsion any longer. But with S, this happens, that if you take something which is S torsion, and twisted by a character, then it will still be S torsion. So this set S was defined by Van Jacob, and he explains this in one of his early papers, that why one takes S rather, why one cannot take the total ring of fractions of lambda G, which may have been what people were trying to do before him. Okay, so we still have this exact sequence from K theory. So K1 of lambda G, and we have this localizations. As I said, this localization is simply to define the localization as you would in a commutative ring, and even though it's non-commutative, S satisfies enough kind of compatibility so that it all is well defined. And again, this is the Grothendieck group of bounded complexes of finitely generated projective lambda G modules, whose cohomology this time is S star torsion. What that means is that when you extend scalars to lambda G S star, you get something that's acyclic. Okay, all right. Okay, so again, you can take complexes now for in general for non-commutative rings or groups G, which are sort of much bigger than gamma. I mean, in the sense of two-dimensional p-adic Lie, two or higher dimensional p-adic Lie groups, you need a stronger condition. You are not. It's no longer enough to say that the module is torsion, but you need it to be a star torsion, which is something stronger. But as long as you have such modules or complexes, they have classes in they give you a class in this relative K0, and you can define characteristic element to be any element in K1 of lambda G star that maps under this boundary map to that particular class. Okay, so you have a way of defining characteristic element even more generally now. Okay, so that's one part. That's kind of attaching arithmetic invariant to some arithmetic object. Okay, Selmer group, let's say. But now we have this weird thing, K1 of lambda G star. How do you get numbers out of it? Okay, that's the other part. Like, how do you get the analytic information out of it? So this is the evaluation of elements in K1 of lambda G star. So yeah, this is third reason why this S star is a nice group. Well, if you have any representation that takes so because G is compact, any representation into QP bar will take values in a finite extension of Q, and you can always take an isomorphic thing which actually takes values in the ring of integers of that finite extension. So this doesn't you're not losing any generality by assuming that rho takes values in GL and OE. Okay, and one can show that actually what you this rho, so you can extend rho to a map from lambda G to Mn of OE. And then you can extend it to lambda from lambda G to Mn of OE tensored with OE double bracket gamma. Okay, by simply sending G to rho G tensored with, so G bar here is the image of G in gamma. Remember that gamma is a quotient of capital G, right? And so eventually you get a map from this thing into this this particular ring, and that induces a map on the level of K1s. Okay, this is total ring of fractions of OE double bracket gamma. So you get a map like this. Okay, and K1 of this MNE is same as K1 of just the 1x1 matrices, which is same as the units here. Okay, so you get this map, and now you can compose this with the augmentation map, and sometimes the augmentation map will not be defined, so you get infinity sometimes. So there are elements of K1 lambda G star can of course have pole, but at least it's all well defined that you get a map like this. So from elements in K1 of lambda G star, you can actually get numbers out. Okay, so I'm not going to go into the statements that one can make for in the non-commutative case. You can now imagine what a statement will look like. you on one hand, you will have an arithmetic object to which you attach characteristic element through this. Okay, you will have an arithmetic object here to which you attach an element in K1 of lambda G. And you can say that actually you can choose this element of in K1 of lambda G S star in such a way that through these evaluation maps, you get L values out. Okay. So that's the nature of a main conjecture in non-commutative Iwasawa theory. Okay, so so again, one can formulate and prove in many cases that the non-commutative version of the theorem of Wiles, which is main conjecture for totally real fields, holds. Okay, and of course, if you assume some vanishing of mu invariant, you can show that it always holds. And you can formulate main conjecture for elliptic curves and so on, and those things are wide open. Okay. All right. So yeah. So instead of telling you about main conjectures in non-commutative Iwasawa theory, I'm going to tell you about some other refinement of Iwasawa theory in a different direction. So on one hand, you can ask if, I mean, this exact sequence, there's nothing special about 1 and 0 here. You can also have K2 of lambda G to K2 of lambda GS star to the relative K group and so on. I mean, for higher K group, it's not clear whether the maps are surjective or not. Nevertheless, you can always kind of you have at least this portion of the exact sequence with sort of Km and Km and then relative Km minus 1. And you can ask, are there arithmetic invariants in the relative Km minus 1? And are there analytic invariants that give you a precise lift, a specific lift of those arithmetic invariants? And this is, I think, a very interesting question, and I have no answer to that. There is some precise statement towards such a conjecture in the thesis of Maltevite in the function fields case. Okay, so he works he works with function fields over finite fields, and he kind of hints at such a conjecture with higher K groups. And if this intrigues you, then you should look at his thesis to see what the nature of such a conjecture could be. But I'm going to give you refinement in a somewhat different direction. And it is possible that these two things are related, but again, I don't know in precisely in what way. Okay, so up to now, we have been kind of studying modules with support in codimension 1. And what the approach, what it does is it sort of ignores everything that has support in codimension 2 or more. Okay, so very small modules are ignored. I mean, what are usually called pseudo null modules. So a question to ask is can analytic invariants actually tell you about these smaller modules, pseudo null modules, and so on? And there's at least on the arithmetic side, you can attach some invariants using higher K groups, but we don't know much about what the analytic invariants should be in this case. Okay, so whatever follows is joint work with these 6 people. Frocke, Ted Chinberg, Ralph Greenberg, George Pappas, Romer Sharifi, and Martin Taylor. Okay, so again, I go back to commutative ring. I mean, this subject is kind of very new, and we don't even know how to formulate things in general. So there is something we can do with non-commutative rings, but very little, and so I'm not going to say anything about that. In fact, I'm just going to restrict to a local commutative ring lambda. If you want, you can actually just take lambda to be ZP, double bracket a bunch of variables. Okay, so power series in infinitely many variables over ZP. Y is simply spec of this ring. y superscript m, these are all codimensional m points of y. So if you like height m prime ideals of y, ZMY is just the free abelian group generated by ym. Now, what we want to study are bounded complexes of finitely generated projective lambda modules, which are exact in codimension less than m. Okay, so what this means is that if I localize at any prime ideal of height less than m, my complex becomes acyclic. Okay, so m equal to 1 is the case that we had been studying earlier. Okay, this is just a piece of notation for any point y in capital Y. C sub y is this localization of the complex. Then I can define the mth Chern symbol, that's the name because it's related to Chern classes, to be this particular thing. Oh, this should be C sub y. I'm so sorry for this typo. Yeah, there should be a C sub y here. Okay, so you take length of lambda, length of these. So I localize it at any height m prime ideal y. So this should be C sub y. I take the cohomology of that cohomologies of that complex. There are only finitely many terms because C itself is a bounded complex. I take length of those cohomologies. And then okay, sorry, I forgot the sign here. Sorry, I hurriedly typed these last parts because I couldn't get my hands on my iPad. Okay, so this should be -1 to the I here, and I take the alternating sum of these lengths. That's my numerical invariant. Yeah, sorry, there are so many typos in this formula. Yeah, I'm very sorry. There should be a -1 to the I here, there should be a y here, and there should be a y here. Okay, because I want it to be an element in this free abelian group generated by points in ym. So there should be a y here, there should be a y here, and -1 to the power I in the second sum. All right. So basically this measures length at height m prime ideals, this mth Chern symbol. Okay, now let's look at what the first Chern symbol is and how it's related to the things that we had been talking earlier. So there's the tame symbol map from K1. Okay, so in this case here, by the way, there are no higher K groups, or there are no K groups at all. Okay, this is just some invariant that one attaches to complexes with support in codimension m or more. So let's look at what happens when m is equal to 1. Okay, we can already bring in some K groups. So there's a map from K1 of Q lambda, which is simply the units in Q lambda to this. This is just the divisor map, right? You take any non-zero function, you just look at its the order at any height 1 prime ideal, and you take that linear combination. Okay, all right. So how is this related to what we had first? If we take the first Chern symbol of x, then you can obtain the first Chern symbol of x by mapping the characteristic by mapping a characteristic element of x under this map. Okay, so the first characteristic element tells you about the first Chern class. Of course, this char x, that's an ideal, right? It's not a well-defined element in here. It's only well-defined up to units in lambda. And what the analytic side of the main conjecture tells you is that you can actually get a nicely defined element in Q lambda that also interpolates L values. Okay, so another way of saying this is that L values actually tell you something about the first Chern symbol of x. So you can ask what happens more generally. Are there invariants in the higher K groups related to the mth Chern symbol? And so at least one can formulate some question, some well-defined question, but we don't have enough analytic invariants to say anything about this. But there is one particular case where we can actually prove something, and I'll come to that on the next slide. Okay, so so what you do is you take, so P sub m of y, these are all m+1 tuples such that the codimension of eta I is I, and the I+1th point lies in the closure of eta I. Okay, so if you like, you have a bunch of prime ideals such that eta I contains the prime ideal eta I+1 and so on. Okay, so I put k sub small k eta I to be the total ring of fractions of this quotient ring. Okay, so this is the total ring of fractions of lambda mod eta I. And then I have these same symbol maps. So for any tuple eta, for any, sorry, this should be eta underscore like this one. So for any tuple eta underscore, I get tame symbol maps which kind of keep going down with each eta I that I choose, and eventually at the mth map will take you to k0 of something which is actually just z, right? So I can put all these things together to actually get a map from several copies of km of q lambda to zm of y. And this is not a typo for once. This is actually p to the m-1, even though I'm working with m. This is because for any codimension m point here, the map that I take is the one, sorry, this should be new. This is a typo, sorry. This should be new of eta bar comma y. So this is so eta is a m tuple, and then you add y to it, so you get an m+1 tuple, and that's what you evaluate. That's what you apply to your element A, and then multiply it by y, and that's how you get an element in this free abelian group generated by ym. Okay, so there is this nice map. Now this is the group where the Chern symbol lives, and you can ask, you can ask, is there a nice pre-image to this? So what does nice mean? Well, something that you can describe, hopefully in terms of some analytic invariance. Is there a nice Chern, is there a nice lift to this? So that's what we define. This is just repeating what, along with the typos, of course, from the previous page. So you define the mth characteristic symbol of m. So m is a module supported in codimension bigger than or equal to m, to be any element xi m in this group, such that nu m of xi m is the characteristic symbol is the Chern symbol of m. Okay, so this generalizes the notion of characteristic element that we had in m equal to 1. Okay, all right. So right, so the question, just to repeat the question one more time, is there an analytic description of this? Okay, and the term analytic, I suppose, is used rather loosely here. I mean, some explicit description of this psi m. Is there a way to canonically choose this psi m? Yeah, in some way. So I mean, I would be happy with sort of an answer which any sort of answer to this. Anyway, so we can do it for m equal to 2 in a very particular case. I mean, we can prove a somewhat more general result than this for CM fields, but maybe the answer is not as satisfactory. So we can describe second Chern class of certain objects. And again, I'm not going to give you precise statements here, but only nature of the answer to this question, okay? And not a precise statement, because I don't want to give the precise definition of Katz's p-adical function, for example. So what I do is I take an imaginary quadratic field in which P splits completely. So P is some odd prime as before. and I want it to split completely in E. So this is what is called the ordinary situation, okay, and not the super singular situation. So in this case, we have these Katz's p-adic function. F be a finite extension of E, which contains mu p, pth roots of 1. Psi be a character of this Galois group of F over E, and I assume that order of psi is prime to T as before. Okay, if this is not the case, then it's not clear what exactly to do. But I mean, this is like Iwasawa theory was in its early days. So hopefully, when maybe there will be generalizations of this without the hypothesis. And kind of for simplicity, I also assume that psi is not the trivial character or the Teichmüller character. Okay. E tilde be the ZP squared extension of E. So if you take compositum of all ZP extensions of E, you get a ZP squared extension, right? So E is an imaginary quadratic field. There are no units. I mean, there are no infinite order units in E. So Leopold conjecture holds, and you know the exact rank of compositum of all ZP extensions of E. It's 2. Okay, and then I just take the compositum of F and E tilde. So this is some two-dimensional extension of K. Okay, now over this K, I take the maximal abelian unramified pro-P extension of K. Okay, this extension is supposed to be pseudo-null by a conjecture of Greenberg. Okay, so Greenberg conjectured that this, sorry, the Galois groups, this X is supposed to be pseudo-null as a two-dimensional Iwasawa algebra, right? As a module over two-dimensional Iwasawa algebra. I have to extend the scalar of X to the ring of Witt vectors of Fp bar for some technical reason. But once I do that, I can take the psi component and then the psi inverse omega component of X. So I would like to describe the second Chern symbol of this module on its own and on this module on its own, right? I mean, there's no difference between psi and psi inverse omega. It's just as psi varies over all characters of this group, so psi inverse omega will also vary over all characters of this group. So, so what I would like to describe is the second Chern symbol of X psi. I don't know how to do that. What I know how to do is to describe the sum of second Chern class of these two modules taken together in terms of something analytic. And what is the analytic thing? Well, we take Katz's p-adic function. So this prime P splits into two primes, pi and pi bar, let's say, in E. And so there are two Katz's p-adic function for E, one associated with the choice of pi and one associated with pi bar. Okay, and these two p-adic functions will, you can take the Steinberg symbol of that in the second K group of Q lambda, and those are the element. I mean, that element in the K group describes this second Chern symbol. Okay, so maybe this question is not completely hopeless. Maybe there is in general an analytic description of these higher Chern symbols, and this is just one instance of it that we found. Okay, so I'll stop here.
No immediate questions. The rest of the audience in the room has any immediate questions.
The other audience member in the room has no immediate questions.
Maybe you can also have a look at the chat in the
there's only about 10 people there, so I assume just so.
Nothing there? Okay. Thank you. I found it very interesting. Also, the more abstract point of view, and then also the generalization, which I've certainly not seen yet. Yeah, I think we'll thank you again.
Okay. Thanks.
In the room, with the the lecture and maybe more audience members.
Same Zoom link.